Welcome back. Takuchi method suggests the use of SN ratio to be the quality measure for robust design. And SN ratio is a function of mean output and standard deviation. Therefore, in the experimental design, we need to use a sampling to decide the average and the standard deviation of your output distribution. Last session, we mentioned the use of outer array to get a better estimation of mean and standard deviation. In these sessions, I would like to use a case study, which is a nominal the best design for cantilever spring, to illustrate how to use the closed array design and how to use the two-stage optimization in the nominal the best problem. Here for the closed array experimental design, we are using inner array to assign the control factors, where each row will stand for a possible combinations for design. And we use outer array for noise factors. Each treatment of the outer array will represent a sampling conditions happen on your design. So we are using factorial design for the outer array to reduce the number of sampling, but still maintain the balanced sampling strategy. This is the arrangement of the inner and outer array. As we discussed before, the inner array is for the design factor or the control factor. For each design, we need to do sampling where we are using outer array to arrange the noise factors to represent the possible sampling for your design. And from the outer array, we can calculate the mean output standard deviation and therefore estimate the SN ratio of your design. This is the cantilever beam examples. Assume we want to design a cantilever beam which can be a spring. And we would like the spring constant for this cantilever beam to be 1 gram per millimeter of diffraction at the tip. So this is the nominal the best problem. In this example, we are using this spring constant equation to be the data generator to simulate the experimental process. Here we have an initial design. If you substitute this number into the equation, you will find out the initial design will satisfy the target requirement where k is equal to 1. And this is the material property. So you want to use a robust design to see if you can find a better design which also satisfies the design requirement, but the quality performance will be better than the initial design. This is the experimental design where we have 4 control factors, and we factorize these control factors into 3 levels according to their design range. But for the material property here, this is the modulus of elasticities. This is the discrete variable because it stands for the material property. So you can only find the material and find out what is the corresponding Young's modulus for that particular material rather than just assign any Young's modulus and try to find a material to fit your selection. So here we select 3 different possible materials and find the corresponding Young's modulus to be the 3 levels of the material property. Because we have 3 levels for each factors, and we have in total 4 factors, so we select L9 to be the inner array. And this is the experimental layout for these control factors. You can assign the level value from the table to the experimental design, and you should be able to complete the design treatment for each inner array. As to the noise factors, we considering only 3 manufacturing noise factors, which are the tolerance for thickness, width, and length. And because we only have 3 noise factors and we assume 2 levels for each noise factors, so we need only L4 to assign these 3 2-level noise factors. And according to our selection, we usually put the lower limit, which is the minus tolerance to be the level 1, and the upper limit, which is the plus tolerance, to be level 2. And you can assign the number into the experimental design, and you will get the outer array as follows. So you can arrange inner and outer array into this kind of format. This is done by using Excel, and I will explain how to do that in the next sections. The inner array is arranged over here, and the outer array is over here. But as you can see, the outer array is transposed compared with the inner array. So for each row of the inner array stands for different design. And for each design, we have several sampling. In this case, will be 4 samples. And each sample is a combination of the L4 outer array. For the first sample, this is under the inference of B to be minus 0.03, which stands for the low limit of the manufacturing tolerance. Same thing for L and H. So for the first treatment, which has the control factor design like this way, and at the first sample, we need to consider the inference of the noise factors. So the actual values of each control factors will be slightly shifted due to the manufacturing errors. Then you can substitute the actual value. For example, B, the nominal design is 4 millimeter, but in the first sample, the B will be influenced by the noise factors, which will have the minus 0.03 tolerance. And then the actual value of B will be 3.97 during the first sample. Same thing for factor L and factor H. So by substitute the number into the equation, you will get the spring constant. However, in the real experiment, this number has to be obtained by doing the experiment. But in this example, we're just using the equation to obtain the data. Following the similar principle, you can get the second and third and fourth samples according to different inference of the noise factors. So this is the reason we want to arrange the outer array in a transposed way, so you can find out the 4 samples for the first design and calculate the mean output for the 4 sample and the standard deviation and the SN ratio. Since this is a nominal the best problem, so the SN ratio will be this equation. Following is the similar process. You can calculate the response table for each control factors. Following the similar method we showed you before. So you can obtain the response table. Here we would like to make 2 response tables and also 2 effect plot according to the mean output and also the SN ratio, because this is the nominal the best problem. I will explain why we need to do that. So the first one, we are using the mean output to obtain the response table. Similar process can be applied to the SN ratio output, and then we can obtain the response table for the SN ratio. This is the effect plot for the mean output and the SN ratio. And select B3, H3, L3, and E1 to be the optimum design where the SN ratio will be maximized. In this case, you can do the experiment for using the outer array to find out what is the performance for this maximum SN design. So you can obtain the K will be equal to 0.89, standard deviation, and the SN ratio 26.7. However, this is a nominal the best problem. In our robust design process, we simply use SN ratio to be the objective, where SN ratio stands for the average quality loss. Certainly, this design will have the smallest quality loss, average quality loss. However, this is a nominal the best problems. We prefer the K, the average output K, to be at 1. But in this current design, the K is 0.89. So Taguchi methods suggest if that is possible, we can find an alternative design which has the similar output, SN output, like this one. However, the mean output can be adjusted to the target where k is equal to 1. So the problem is, how can we do that to maintain our result for maximize SN but move our design target to 1, which I will explain in the following section.